The year is 2015. It is the time of great innovation and advancement in almost every area of science and technology. Over the past 30 years, our lives were transformed beyond recognition. The rate of progress in everything from personal computers to the internet, from mobile devices to social networking, made us expect technology to get better, faster, and simpler every year. We expect it everywhere, except for pharmaceutical and medical interventions. But most of the pharmaceutical companies have been stalling and failing to create new breakthrough therapeutics despite continuously increasing costs. And while there are many challenges impeding progress in biomedical sciences, one of the main problems is testing the many therapies on human patients to understand if they work and how they work. But unlike in information technology, there is no way to do it quickly and cheaply. Preclinical and clinical studies take decades, cost billions of dollars, and fail in over 90% of the cases. That is why pharmaceutical companies try to play it safe and make marginal improvements instead of betting big money on revolutionary technologies. And in the world of preventative medicine, the situation is even worse. Healthy people just don't want to be guinea pigs and experimented on. Nobody in the right mind will give their healthy body to an academic institution or to a pharmaceutical company to test the long-term effects of possibly harmful drugs. But if we look back into history, some of the major scientific advances were made by scientists experimenting on themselves. From ancient Egypt, Rome, China, to very recent past, scientists were always tempted to test their hypotheses on themselves when other subjects were not available. In 1984, Barry Marshall drank a petri dish of the Helicobacter pylori from a patient and soon developed gastritis, achlorhydria, stomach discomfort, nausea, vomiting, and halitosis, fulfilling Koch's postulates. He was awarded the Nobel Prize in Physiology or Medicine in 2005. But most of the contemporary scientists working on new biomedical technologies have pure academic interest. They want to advance science by publishing their studies in academic peer-reviewed journals and get recognition at conferences and in popular press. Just Google anti-aging drug in the news, and you will get millions of results. Most academics do not take any of their own drugs and condemn all kinds of self-experimentation. They leave it up to the pharmaceutical companies to build on the fruits of their research. But some of the scientists with deep knowledge of some of the drugs and access to laboratory equipment are convinced that we do not have the time to wait, and they are willing to test their hypotheses on themselves. This practice is called academic self-experimentation. They routinely measure a broad number of vital parameters, from basic biomarkers and full-body MRIs and CT scans to complex medical checkups by their colleagues. Some of them try the various drugs on a long-term basis and conduct longitudinal studies. Some try the effects of the drug only once or several times to estimate its effects on blood biochemistry or cell counts, or look at the combination of drugs to check how these drugs interact. Some of these scientists go to great lengths in their self-experiments. While pharmaceutical companies may measure just a few markers when conducting clinical trials, these scientists measure and store the many tissues to understand the long-term effects.
Some of the drugs that work in diabetics may have life-extending effects. But the reason why we're taking those drugs is not to try to extend our own life. The idea is to test the effects of those drugs on as many biomarkers as possible. I am willing to self-experiment, and I'm willing to share this data honestly.
Unfortunately, there is no way to publish these results in scientific literature and high-class peer-reviewed journals because self-experiments are considered to be biased and despite a large number of markers, the sample size of one patient is considered too small, especially when the patient is healthy. Another problem with publishing these important results is medical insurance companies. These companies do not want to be responsible for medical bills from patient-inflicted medical problems. Imagine that one of these scientists develops cancer. The insurance company may terminate their policy because they find a publication where this scientist disclosed that he or she was taking a potentially cancer-causing drug. Scientists need a place to publish their self-experiments, but in a way that does not diminish their academic reputation or cause problems with medical insurance companies. The advent of online open-access publishing led to many advanced new publishing models where academics can perform interactive peer review, interact in a closed social network, discussing their concerns. Some journals make the reviewer names and affiliations visible on the publication after peer review is over, and some allow post-publication discussion and review. One of the best journals in open access publishing is Frontiers. They run tens of high-quality peer-reviewed journals on their platform and enable scientists to engage in interactive peer review, track each other's progress, and communicate with each other. We want to build on best practices of these journals and allow scientists to publish their self-experiments, discuss their results, and deposit vital biomarker data into a special repository. But in addition to all the best practices of open access publishing, we will give these brave scientists the ability to publish under a pseudonym. At least one author on the paper must have a real name and affiliation. Scientists will have the ability to revert to their real name at any time. This is done to ensure that the insurance companies do not discriminate against the pioneers who are trying to make this world a better place and are willing to risk and sacrifice to achieve this goal. But we would like to make sure that only credible MD and PhD level scientists can get their results published. That is why we would like to ensure that at least 2 members of the editorial board approve the author before any submissions or experiment proposal is accepted. We would like to develop a comprehensive repository of biomarker data to make sure that the data is structured and can be visualized and reanalyzed after it is published. We also envision the creation of a virtual experiment assistant that will enable scientists to log their experiments in a lab book, upload various types of data coming from different labs in different formats, and standardize their results. The system will take at least 6 months to develop, and we estimate the development costs around $300,000. We will also need at least 2 full-time staff members to coordinate the activities of the journal, communicate with the scientists, and maintain the system, and we estimate the labor costs to run up to $200,000 in the first year of operation. That is why we need to rely on your help to make this happen and accelerate the propagation of laboratory discoveries into clinical practice. You will be making a difference in this world, and we prepared a list of rewards and recognition options to make it worth your while.